So we're going to spend some time looking at the solid state. We're going to look specifically at what are called crystalline solids. There are basically two ways to categorize solids, and the crystalline solid has stuff that we can actually work with, calculations we can do. Within this discussion, we'll define something called a unit cell. So let's first define a crystalline solid. A crystalline solid has a regular repeating pattern to it, okay? So it's a long-range order. You will see a piece of it get repeated over and over and over again. That's what a crystalline solid is. If it's not a crystalline solid, then it's going to be an amorphous solid. And it does not have any well-defined long-range order. So I want you to imagine that you've cooked spaghetti and you've drained it and you've let it sit on a plate for a while without sauce, and it all congeals together, and you grab it and pick it up and it's a big wad of spaghetti. That lacks any type of long-range order. It is a jumbled mess. A lot of your really long molecules are plastics, and that's how they are. They are a lack of long-term order. They are like a plate of spaghetti that has congealed together. There's not a whole lot of work you can do, simple calculations you can do with amorphous solids, but we can with crystalline solids. So crystalline solids are all based upon what's called a unit cell. And the unit cell is that little piece that gets repeated over and over and over again. It is that basic repeating structural formula. And there's a lot of different types of unit cells, and that's what we'll see on this next, oh actually no, we won't. We'll see it in a minute. So if you look at the bottom left of this slide, you'll see what we call a unit cell. And it gets repeated over and over and over again in 3 dimensions, and that makes your full crystalline solid. So that'll get repeated so often that you will actually see that shape in the crystalline structure when you look at it with your eyes. Now I've got little black points in here, and these little black points that you see, or also over here in the full crystal, are called lattice points. And lattice points could be made up of a lot of different things. A lattice point might be an atom. Okay, that's what a lattice point could be. It could be an ion sitting there at one of those points, or it could be a full molecule, okay? So a molecule might be repeated over and over and over again, just depending upon what kind of crystal we are talking about. Now we have lots of different types of unit cells, and you don't need to memorize this slide, okay? I just show it to you so that you can see all the different types we have. Let's focus on the simple cube just for a moment, because that's the one that you really will need to know. And a cube, the length, the width, the height, they're all the same. So that's what's being said here. The length, the width, the height, they're all the same. And all the angles are 90-degree angles. So that is a simple cube. But you can see that if we start changing pieces of it, here in this one, 2 of the sides are the same, but one of them is different. And so we see that planning out in that structure, but still everything is 90 degrees. So kind of you might want to pause and look at each one of those and just kind of note what's similar, what's different versus the simple cube. But like I said, you don't need to memorize them all. We will focus strictly on the simple cube for our work in this class. So here's a simple cube, and I want to kind of focus on that. We've got a repeating pattern over and over again of what you see right here, okay? And I'm going to actually, see if I can make that right there, okay. So I'm going to write on the light board here for a moment, and let's kind of get a feel for what we're looking at. So we're repeating over and over and over and over again, okay? And this is our simple cube. But that is showing the lattice points as if they're dots, and they really are not dots. Those lattice points are atoms that are bumping up to their neighbors, okay? So they're all, and I'm not drawing this very well at all, but they're bumping up to their neighbors. And so what you see in the middle image on the PowerPoint slide is those being filled in. We often look at it this way because it's easier for us to see what's in front and behind that way. Now, this whole thing, including all the atom, is not the unit cell. It's just what's getting repeated over and over again. And image C is what is actually getting repeated over and over again. So I'm going to show you image C in 3 dimensions here. Okay, so I'll turn it around for you to look at. This is the actual unit cell of a simple cube. So we would see the lattice point as if it were right there on that point, okay? But that's just the middle of the atom. And if we took one of these cubes and we put another one right next to it, okay, then we'd start filling in this circle to where you'd have a, well, you can't see that anymore. Slide up there. So you'd see the whole atom, okay, if we put all of these unit cells together around there. So that is a simple cube. So I said we're going to focus on cubes. They're not all simple cubes, but this is a simple cube where there's one lattice point in each one of those corners. There's a term called coordination number, and the coordination number is how many atoms this guy is actually coming in contact with. Okay, so this guy right here is actually coming into contact with him, and he's coming in contact with him, but he's also coming in contact with other atoms that are in the unit cells around there. So when you talk about crystalline solids, a lot of times coordination number is one of the terms that we will utilize. Here are the 3 types of unit cells that you're actually going to have to commit to memory. Okay, there's the simple cube, of which I just showed you in detail, and we'll look at the other ones in more detail. You'll notice that in this image, they are not showing just the unit cell, they are showing you more of it than it's got. So the unit cell is actually just this part, right? But it's got those atoms all around them, and we're gonna dissect this here in a minute. Okay, I don't want you to memorize those numbers. The coordination number, the one that's got the best coordination number, is a body-centered. So let's just focus on the body-centered for a moment. Notice how there's a yellow atom right there in the middle. Okay, let's see if I can make this pointer work. This is a new thing that oh, there it is. So that guy right there in the middle is the centered in the body, and we call that a body-centered. And then you've got the face-centered. So you've got these guys that are here on the top, the bottom, each face. And how many faces does a cube have? Well, it's got 6 faces, so we have 6 of those guys around there. So that's the coordination number, and the face-centered has got the highest coordination number. The next one is a relationship between the radius of the atom, okay? And what's the radius? The radius goes from here to the outside edge, or from here to the outside edge. That's the radius, okay? And the edge length, okay? So the edge, EDGE, equals 2 times the radius. And it's easy to see it here. If this is a radius from here to here, and this is a radius from here to here, okay, 2 of those make an edge length. Well, with a little bit of geometry, you can get that relationship between the radius and each one of those edge lengths. So those are the equations that get you the edge length depending upon which one of those cubes you have. Now, sometimes you're given the radius and then you have to do some calculations, but in your calculation you really need the edge length, so you've got to use those calculations. You will not have to memorize these for my class. I do want to note this in case you have to use it for a calculation. You see that square root of 2? That square root is only over the 2. It's not over the r. A lot of students see that and extend that square root bar over the r. It's 2 times the square root of 2, and then times r. The last thing we see here is the efficiency packing. It's how closely they're packed together, how much atoms versus empty space. And as the coordination number goes up, the efficiency goes up. Again, you don't need to memorize that, but only 26% of this structure is empty space, whereas up here, 48% of it is empty space. So that is just what efficiency packing is. We're going to spend some time right now talking about this part, how to determine that there is one atom in a simple cube. Because I can tell you that when I look at this, and I don't know if this, oh it does, it erases when I go backwards. When I look at that, it looks to me like it has 8 atoms in it. But when we remember that the unit cell is not the full atom, but only a portion of the unit atom, we'll see how that comes up with the number 1. All right, I already talked about that. Let's look at this. If you focus on the dark blue box, focus on that dark blue box, that's 1 unit cell. And I want you to look at that little atom that I've got the black arrow pointing to. And tell me, you might have to pause and study this a while, but I want to know how many unit cells is that atom being shared between? Well, hopefully you said 8, okay? So if that is 8, and let's see if we can, actually I want to go back and let's look at it, and let me write on there. How can we look at this? This unit cell is in the back right of my image. Do you agree with that? And there is a unit cell sitting in front of it right here. Okay? Would you agree that that atom is both in the back one as well as the one in front? Okay? There's also one over here which is in the back left. Okay, you're in the back left right here. That atom is being shared in that unit cell. In this front, okay, coming back and along here, I don't know if I'm drawing that very well, but in this back front, it disappeared. Where'd it go? I don't know. Hang on a second. I'm going to get there. Oh, there it is. Okay, so if we just look at the top, there are 4 unit cells that atom right here is sitting in. And if we have 4 on top, there's also 4 on bottom. So it's being shared between those. So what we have there is it being shared by 8. Okay? Now, keep in mind what we have. If this little atom right here is being shared by 8, it is only 1/8 in the unit cell. So let me pick up my little model here again. And let's focus on this guy right here. Okay? He is in this unit cell. He's in the unit cell sitting right beside it. He's in a unit cell above it. He's in a unit cell that's coming in at a diagonal to it. Okay, that's 4 unit cells. This guy right here is only 1/8 of a sphere. If you were to take a styrofoam ball, now if you could get a hold of one, okay, and just cut it in half, and in half, and in half, okay, you end up with 8 pieces. You could take those 8 pieces and make a sphere out of it, or you could rearrange them, and that's all they did to make this, is they took those 8 pieces and they made them each in a corner. So this corner is just 1/8 of an atom. And you need to know, first it's helpful to remember it if you can visually see it, that a corner atom in a unit cell only counts as 1/8 of an atom. Okay, so we'll keep that in mind. All right, we'll keep that in mind and let's go to our next image. This is the image of a body-centered cube. Okay, in a body-centered cube, you've got the atoms that are in the middle of the sphere. So let's look at my model here that I have. And we have the corners, okay, of which we still have 8 corners, and each corner has only 1/8 of an atom associated with it. And then we have this guy right here in the middle. So if we wanted to count how many atoms was in this unit cell, we could memorize it, but I'm never about memorizing. I'm about understanding. I know my corners are each 1/8, and there's 8 corners. So 1/8 times 8 is 1 atom. And then this guy is sitting fully in the middle. He's not sharing with anybody. He is completely in the middle. So that is 1 more, and that gives us a total of 2. So that's what we have written right here on our screen. This is for our corners, okay, and that would be the purple. And this is for our center, which is in this diagram, yellow. Okay, so that would be a total of 2 atoms in this unit cell. Next one, I already stated that, but you can write that down. Oh dear, I think I just tore up my unit cells. All right, let's go to the next one. This is our face-centered cube, okay? And boy, doesn't that look pretty complicated when you're looking at all the pieces and the parts. But what we have is a face, okay, and there's my face with the purple on 4 corners. But there's also one right in the middle of that face, okay? And each face has one in the middle. So this is the top face, it has one in the middle. Here's the right-hand face, it has one in the middle. The front face, it has one in the middle. The back face, you see it back there? It has one in the middle. The left face, it has one in the middle, okay? And the bottom face, it has one right in the middle. Now, if you look at the unit cell, you'll see that each face is being shared by 2 unit cells. So let's look at my model here, okay? If we look at this big red one here, he's in this unit cell, and if I brought in another box just like it, he'd be sitting in this unit cell. It's just being shared by 2. So each one of these is a half of a circle, okay? So we count this as a half, this is a half, this is a half, and then all the other ones. There's one on the bottom, there's one in the back, on both sides, okay? So each one of those would count as a half. So if we wanted to add up how many atoms are in this unit cell, we would simply have to remember that a corner is an eighth and a face is a half. If you can see it, it's easy to remember. If it's just a memorized number, it's easy to forget. So we will, oh, I'm not very kind to my models there, am I? We will look at our numbers here, okay? So we've got our corners, okay? There are purple in this image. We've got our faces, which are yellow in this image. There are 8 corners, each counts as 1/8 of an atom. There are 6 faces, each counts as a half of an atom. So a face-centered cubic cell has a total number of atoms of 4. Now some of you are great at memorizing, and you could memorize that number. The thing about memorizing that number is it's easily remembered and easily forgotten. And the concept is what I really want to drive home. So here's kind of a summary of the 3 that you are responsible for, okay? You need to know the names of each of them. You need to know what they look like. And you need to know, lastly, how many atoms are in each unit cell. And of course, my preference for long-term memory is that you understand why those numbers are what they are. And that's why I spent some time doing that. Now, when you have an ionic solid, and I'm going to go back to my light board here, and I want to draw a sodium chloride unit crystal, okay? So we would have an Na, and it's positively charged, sitting next to a Cl minus, which is negatively charged. And that would go off in 3 dimensions. Cl minus, Na plus, so that's going off this direction, and then for every sodium, it would be surrounded by 6 chlorines. 1 below, 1 above, 1 to the right, 1 to the left, 1 in front, 1 behind. But I can't do the front and behind. I'm not going to try doing that. All right, so we've got our crystal growing here. Repeating pattern. It is definitely a simple, well, it's a cube. I'm not going to say whether it's simple or what. But it is definitely cube, and if ever you looked at a salt crystal in your hand, if you've never done that, use that curious brain of yours, and next time you put salt on your French fries, look at a crystal and you will see that it's definitely got this cube structure. Now what would be easy to think is that the unit cell is, I'm going to do one more here, okay? It would be easy to think that the unit cell is what I'm going to outline in yellow, okay? It would be easy to think that we are just repeating this over and over and over again. Well, in an ionic solid, that is not how you do a unit cell. The way you do a unit cell is to go from one atom until you're repeating that thing over and over again. If you repeated that thing over and over again, you'd see the same thing. So if I take this guy and repeat it, it has chlorine in the left corner and sodium in the right corner. Is that what I have here? No, I have sodium in the left corner and chlorine in the right corner. This is not a repeat of this, okay? What is a repeat of it? What we need to do is go from here all the way to here. So let's see if I can kind of ignore those lines, okay? Get rid of those lines, and what do we see? This is what's getting repeated over and over again. Chlorine is in the top left and the top right, and the sodium is right in the middle on what we call an edge. If I repeat that, I have chlorine on the left and on the right, and sodium in the middle. What's in the very middle of the cube? A chlorine atom still. So this is what gets repeated over and over again. So it's not like every ion is the lattice point. We're going to have to repeat it over and over again. We've got these body centers, and we have something new called an edge, okay? So when we look at an ionic solid, there's something that if we had an ionic solids unit cell, and I don't have the full unit cell of this thing out, but I do for the cesium chloride there. When we look at that getting repeated over and over again, we should be able to determine the formula of that molecule, of that ionic compound. So let's see how to do this with the cesium chloride. In the cesium chloride, we have the cesium in the middle of the unit cell. So I ask you, how many cesium atoms are in this unit cell? There is one cesium, okay? So cesium, there's one. It's in the middle. Chloride ions, how many Cl- ions do we have? Well, the rookie would say, well, there's 8 green spheres there, therefore there's 8 atoms. But we know that each one of these corners are only 1/8 of an atom, right? So if there's 8 of those corners and they each count as only 1/8, it's 8 times 1/8, and that equals 1. So in this unit cell, there's one cesium ion and there's one chloride ion, and that would tell me that CsCl is the formula of this compound, which you could get by doing a look at the charges on a periodic table, but that's how you do it using the information of a unit cell. Let's look at the right-hand side. This is the unit cell of a zinc blend, okay? And it's got something, no it doesn't. It doesn't have an edge. So we do see something a little bit different here, and that is, well, let's see what we have here. Let's count up how many of each of these things we have, right? So let's start with the zinc. This zinc atom is completely inside of my cube, okay? If I were to draw my cube, that guy is completely inside of that. And how many of them are there? Well, there are 4 of them completely on the inside. So if we're going to count the zinc ions, we see that there are 4 completely embedded inside of there. Now let's do the sulfide ions, okay? And let's see how many we have. First of all, we have, dang it, what have I touched? Let me back up the bus. There we go. The sulfide ions, we have a bunch of corners, all right? So we have ones that are sitting on the corner. How many corners are there? Well, of course, there's 8 corners. And each of those corners are 1/8 of, trying to get used to a new technology here. Each of those corners are 1/8 of, there we go, an atom. But that's not all we have. So there's my 8 corners. 1, 2, 3, 4. Back here, 5, 6, 7, 8. All right, but that's not all we've got. What else do we have? We've got this guy sitting right here. And I want to put a box around him so that we can distinguish him from the other guys. Can you tell where that guy is sitting? How about if I drew this one here? Can you tell where that guy is sitting? Or this one right here? Every one of those is on a face. Now it's hard to see that it's on the face when I've got that line going back there. But there you go. This is sitting on the face with half of it in this unit cell and half of it in its neighboring unit cell. So I have got with the zinc also 6 faces, and we know that each face is 1/2 in that unit cell. And so what does that give me? 4 sulfide ions. So we have zinc 4, sulfur 4, but is that how you leave an ionic compound's formula? No, you always reduce it to its empirical formula, so this also is a 1-to-1. And you could get that from the charges off the periodic table as well. Now, this leaves me with one that you're going to come across, and I want to go to my light board to explain this. And that is sometimes you will have a unit cell. Okay, here's my unit cell. And let me draw the 3 dimensions of my unit cell. Okay. So here's my unit cell. Sometimes when you're dealing with ionic solids, you might have one sitting on an edge. We've talked about corners, okay? We've talked about face-centered and body-centered, but what about edges? I want you to think about an edge of a cube, and if you need to, go get you a textbook and let that be your cube. And see how many, if you have 4 textbooks that are the same size, how many can you stack together that would share one of the edges? Okay? That guy is shared by 4 unit cells. So an edge is 1/4 of an atom. So you might run into that when you're doing work similar to what we've done on this PowerPoint slide, determining the empirical formula of an ionic compound by counting up the atoms in that unit cell. Okay, so what have we done with this lesson? We've talked about crystalline solids. We've talked about how you have this repeating pattern, and that repeating unit is called a unit cell. We know that there's lots and lots of different unit cells, but we focused only on the cube, whether it be a simple cube, a body-centered cube, or a face-centered cube. And we've talked about how to count how many atoms are in that cube. Up next, we're going to start doing calculations using our unit cells.